Welcome back to the Cosmic Atlas, where we navigate the wonders and dangers of our universe, one cosmic mystery at a time. I'm your host, and today we're diving into a threat that's literally staring us in the face every single day. Yet most people have no idea how close we came to disaster just 2 years ago. Right now. At this very moment, there's a dark region on the Sun, larger than 10 Earths. Scientists worldwide are monitoring it with intense focus because history has taught us a terrifying lesson: when the Sun gets angry, our modern world can go dark in seconds. Before we go any further, if you're fascinated by space, science, and the cosmic forces that shape our existence, smash that subscribe button and hit the notification bell. This channel brings you deep dive investigations into the universe's most compelling mysteries. And trust me, you don't want to miss what's coming next. And if this video gives you that wow moment, show some love with a like and share it with someone who needs. To know this story, here's what we're going to uncover. Today, the massive solar storm of 1859 that set telegraph stations on fire across the continents housed 6 million. Canadians lost power in just 90 seconds during a 1989 solar assault. We missed a civilization-ending event by 9 days in 2012, and nobody told you what's happening right now during Solar Cycle 25, and why scientists are more concerned than ever whether the Sun could actually end life as we know it, and what we're doing to prepare. The stakes have never been higher. We've built a globally connected, electricity-dependent civilization in the blink of a cosmic eye. Our ancestors lived without electric grids, GPS satellites, or internet infrastructure. A severe solar storm today wouldn't just be inconvenient. It could trigger cascading failures across every system that keeps 8 billion people alive. This isn't science fiction. This isn't fear-mongering. This is science fact, documented in historical records, geological evidence, and recent near misses that should keep every infrastructure planner awake at night. So buckle up. We're about to journey from the violent surface of our star to the fragile technological bubble we call modern civilization. You'll discover why the same sun that gives us life might also take away everything we've built. Let's begin. Look up at the sun, though, please. Never directly on, you see a perfect yellow disk, unchanging and eternal. But that's an illusion. The sun is a churning nuclear furnace consuming 400 million tons of hydrogen every second. With surface temperatures reaching 10,000 degrees Fahrenheit, and scattered across that blazing surface are dark regions we call sunspots. What are sunspots? Sunspots appear dark, but that's only by contrast. They're actually glowing at around 6,300 degrees Fahrenheit, hot enough to vaporize any known material. They look dark because they're surrounded by even hotter material at nearly 10,000 degrees Fahrenheit. If you could isolate a sunspot against the blackness of space, it would shine with blinding intensity. Ancient Chinese astronomers recorded these dark marks on the sun as early as 800 BCE, believing them to be omens from heaven. In a way they were, right? Sunspots do signal something significant. Sunspots are windows into the sun's magnetic violence. Deep within our star, in a churning layer called the convective zone, superheated plasma rises and falls. The sun's rotation faster at the equator than at the poles twists and tangles. Magnetic field lines like rubber bands being wound tighter and tighter. When these field lines break through the sun's surface, they suppress the normal flow of heat from the interior, creating cooler regions, sunspots. But here's what makes them dangerous. The magnetic field strength within a sunspot reaches 2,000 to 5,000 Gauss, thousands of times stronger than Earth's entire magnetic field in 1755. Swiss astronomer Johann Rudolf Wolf began systematically counting sunspots, discovering they follow an approximately 11-year cycle. During solar minimum, the sun may go weeks without a single visible spot, quiet, peaceful, safe. During solar maximum, dozens or hundreds pepper the surface, and the risk of dangerous solar storms reaches its peak. We're currently in Solar Cycle 25, which began in December 2019. Scientists predicted it would be weak around 115 sunspots at maximum In July 2025, they were wrong. Activity has exceeded every forecast. In May 2024, the Sun unleashed the first G5-level geomagnetic storm in over 20 years, producing auroras visible from Florida to Mexico. In November 2025, ANX 5.1 flare erupted, the strongest of the year, triggering radio blackouts across Africa and Europe. Weeks later, a December flare sent another massive wave of charged particles hurtling toward Earth. Dawn in December 2025, NASA's Solar Dynamics Observatory detected a sunspot region spanning more than 10 Earth widths. Active regions labeled AR429444296 showed complex magnetic configurations that scream danger to solar physicists. Sunspots rarely appear alone. They typically form in pairs with opposite magnetic polarity, one acting like a north pole, one like a south. Magnetic field lines arc between them, rising high into the solar atmosphere. When these lines become twisted and cross, they can reconnect with explosive violence. This magnetic reconnection releases energy, equivalent to millions of nuclear bombs detonating simultaneously. The result? Solar flares, bursts of electromagnetic radiation, traveling at light speed, and coronal mass ejections. CME's billion-ton clouds of magnetized plasma racing through space at millions of miles per hour when aimed at Earth. These events can arrive in as little as 17 hours, carrying enough energy to overwhelm our technological defenses. History has already shown us what happens when the sun's fury meets our vulnerable infrastructure. And that history begins with a quiet English morning in 1859, September 1st, 1859. Dawned clear and bright over Surrey, England. Richard Carrington, a 33-year-old brewer and amateur astronomer, climbed into his private observatory to continue his daily solar observations. He had been meticulously tracking sunspots for years, trying to understand their patterns and movements. On this particular morning, Carrington noticed an unusually large and complex sunspot group near the center of the solar disk. He began sketching it carefully, routine work he'd done hundreds of times. Then, at 11:18 a.m., something extraordinary happened. Two patches of intensely bright white light suddenly erupted within the sunspot group. Carrington later described them as kidney-shaped, blazing with brilliance that far exceeded even the sun's blinding surface. He stared in amazement, unsure whether his eyes were playing tricks. The bright patches moved, drifting across the sunspot group for about 5 minutes before fading away. Carrington rushed to find someone else to witness the phenomenon, but by the time he returned, it had vanished. He had just observed the first recorded solar flare in human history, and the consequences were already racing toward Earth at nearly 1 million miles per hour, approximately. 18 hours later, remarkably fast for Acme, the world began to experience something unprecedented. Auroras appeared everywhere, not just in the Arctic, but across the entire planet. People in Cuba witnessed crimson curtains dancing across tropical skies. Observers in Panama, Japan, Australia, and chilly regions that never see auroras watched in wonder and terror as the heavens seemed to catch fire in the Rocky Mountains. Gold miners woke at 1 a.m. convinced that dawn had arrived. The auroral glow was so bright they began preparing breakfast, only to realize hours later that the sun hadn't yet risen. In northeastern cities, people reported reading newspapers by aurora light alone. The sky glowed with reds, greens, and purples so intense that some feared a massive fire or even war. But the auroras were just the visible symptom. The real chaos was unfolding along telegraph wires across Europe and North America. The telegraph was the Victorian internet, the first technology, enabling instant global communication. Messages that once took weeks could now be sent in minutes. Financial markets, governments, and businesses depended on it completely. On September 1st to 2nd, that system shattered, telegraph operators reported. Sparks flying from their equipment, severe electric shocks when touching machines, telegraph, paper bursting into flames, equipment operating with batteries disconnected the excess electrical energy in the atmosphere was inducing powerful currents. in the long metal telegraph lines. Some operators discovered they could send messages using only the storm's energy, no batteries required. It was both fascinating and terrifying. In the aftermath, scientists struggled to understand what had happened. Carrington himself was cautious, noting the correlation between his solar observation and the geomagnetic chaos, but refusing to jump to conclusions. Over subsequent decades, the connection became undeniable. The sun was capable of producing explosions that could reach across 93 million miles of space and affect Earth directly. Today, we understand the Carrington event was a perfect storm of unfortunate circumstances. Exceptional intensity. The flare released vast amounts of energy in minutes extreme speed. The CME traveled at roughly 1 million miles per hour. Arriving in just 17.6 hours, most take 2 to 4 days. Clear path evidence suggests an earlier eruption cleared the way, allowing the main CME to travel faster and retain more energy. Perfect magnetic alignment. The CME's magnetic field likely pointed southward, opposite Earth's field, maximizing energy transfer. The estimated disturbance storm time index DST reached between -800 and -1750 nanoteslas. For context, the 1989 Quebec blackout storm reached -589. NT Carrington was potentially 3 times more powerful. Here's the unsettling truth. Carrington wasn't unique, just uniquely documented in the modern era. Scientists analyzing tree rings and ice cores have identified massive solar storms throughout history. 774, 775. CE, a storm possibly 10 to 20 times stronger than Carrington, leaving carbon-14 spikes in ancient trees. 993 to 994 CE, another extreme event. Somewhat weaker but still extraordinary. 7176 BCE and 5259 BCE. Additional megavents preserved in geological records. These so-called Mioke events suggest our sun regularly produces storms far exceeding anything witnessed in modern times. The question isn't whether another will occur, it's when. The Carrington event struck a world with minimal electrical infrastructure. Telegraph wires were the only significant conductors vulnerable to geomagnetic currents. The damage was inconvenient but manageable. Within days, the system was restored. But what would happen today? In 1859, there were no power grids, satellites, GPS, internet, computers, or cell phones. The global economy didn't process millions of electronic transactions per second. Hospitals didn't depend on electrically powered life support. Nuclear plants didn't require constant monitoring and cooling today. A Carrington-class event would interact with infrastructure that simply didn't exist 165 years ago. The consequences would be incomprehensibly worse. We don't have to imagine what a solar storm can do to modern infrastructure. We have a recent example, and it should terrify us. March 13th, 1989. Began like any other Monday for the 6 million residents of Quebec, Canada. Most were sleeping peacefully as a massive coronal mass ejection, launched from Sunspot region 5395 2 days earlier, slammed into Earth's magnetic field. What happened next became the most significant. Solar storm impact on infrastructure in modern history. At exactly 2:44 a.m. Eastern Time, geomagnetically induced currents surged through Quebec's power grid. The Hydro-Quebec system, which supplied electricity to the entire province, began experiencing cascading failures. Transformers overheated. Circuit breakers tripped. Protective relays designed to prevent equipment damage began shutting down grid sections faster than human operators could respond. Within 90 seconds, not hours, not minutes, but 90 seconds, the entire system collapsed. 6 million people woke to cold and darkness. The Cascade office. Its buildings went black. Underground pedestrian tunnels became pitch dark. Trapping people, elevators stopped between floors. Montreal's metro subway system shut down completely. Dorval airport closed. Schools and businesses couldn't open for 9 hours. One of North America's largest and most modern electrical systems was completely non-functional. This happened in March, when nighttime temperatures in Quebec regularly drop well below freezing. Without electricity, heating, Systems failed, water pipes risked freezing, and bursting. Water treatment and pumping systems struggled to maintain pressure. Every hour increased the risk of permanent infrastructure damage. The answer lies in geology and geography, a perfect storm of unfortunate factors. The Canadian Shield. Quebec sits on ancient granite bedrock with extremely low electrical conductivity. When geomagnetic currents flow through Earth during solar storms, they normally disperse through the ground. But on the Canadian Shield, the ground is too resistive. The currents seek other paths, specifically power lines, long transmission lines. Hydro-Quebec's system carries electricity from massive hydroelectric dams in the James Bay region, far north, to population centers in the south. These lines stretch more than 1,000 kilometers, acting like giant antennas that collect induced currents during storms. Integrated grid design. The system was designed for efficiency and reliability under normal conditions, but this integration allowed failures to cascade instantly across the entire network. While Quebec suffered the most dramatic failure, the storm caused chaos across North America. More than 200 power grid problems erupted within. Manetze, New Jersey transformer was damaged. Circuit breakers tripped from coast to coast. The United States came frighteningly close to similar. Widespread blackouts, only timing and luck prevented an American catastrophe. U.S. utilities had just enough reserve capacity, and grid configurations happened to prevent full cascade. But the margin was razor-thin. In orbit, satellites tumbled out of control. NASA's TDRS-1 communications satellite recorded more than 250 anomalies as high-energy particles bombarded its electronics. Even Space Shuttle Discovery, which had launched just hours before the storm, experienced mysterious sensor problems that disappeared only after the storm subsided. The storm produced spectacular roars visible as far south as Texas and Florida. Some observers initially feared nuclear attack. Others believed they were witnessing supernatural events. The sky glowed red-green, purple colors southern residents had never seen before and might never see again. Before March 13, 1989. Few people outside specialized scientific circles understood that solar storms could affect power systems. The idea seemed absurd after the Quebec blackout. Nobody doubted it. Dr. David Bodler, who later led Canada's Space Weather Group, called it the biggest geomagnetic storm of the space age. It became the archetypal event for understanding power grid vulnerability. Every subsequent study uses the 1989 event as a benchmark. Hydro-Quebec spent over $2 billion. In the following 6 years, implementing protective measures, raised trip levels on protective relays, installed series compensation on transmission lines, established real-time monitoring systems to detect early warning signs, develop procedures to reduce power flows. Before damage occurs, the investments paid off. Since 1989, multiple intense storms have struck, some approaching or exceeding 1989 intensity without causing similar blackouts in Quebec. The modern system can handle a 1 in 100-year event. But here's the problem. The March 1989 storm was estimated to be approximately a 1 in 50-year event, with a peak DST of -589 NT. The Carrington event may have reached 1,750 in to roughly 3 times more powerful. Quebec's improvements protect against storms like 1,989. They may not protect against storms like Carrington. And we're overdue. Right now, as you watch this video, we're living through solar cycle 25 and it's not behaving as predicted. When cycle 25 began in December 2019, an international panel of experts predicted it would be weak to moderate. Similar to the relatively quiet cycle 24, they forecast around 115 sunspots at maximum, occurring in July 2025. Some researchers even speculated we might be entering a prolonged quiet period similar to the Maunder minimum of the 1600s. When sunspots virtually disappeared for decades, the sun had other plans. From the beginning, cycle 25 exceeded every prediction. Activity ramped up faster than models suggested. By January 2023, just 3 years in cycle 25 had already surpassed cycle 24 at the equivalent point. The increase wasn't subtle. It was unmistakable. During the first week of May 2024, active regions AR-13663 and AR-13664 unleashed a barrage of powerful flares and CMEs. In just 7 days, 82 notable solar flares erupted. 9 were X-class, the most powerful category. Multiple CMEs launched toward Earth in rapid succession. The CMEs arrived starting May 10th. Bunching up in waves due to the rapid-fire nature of eruptions, they created a G5 geomagnetic storm, the highest rating possible, the first since 2003. The May 2024 storm produced one of the most spectacular aurora displays in recorded history. North America, visible from Florida, Texas, New Mexico, Arizona VIN, the Florida Keys and Yucatan Peninsula RUPUP, as far south as Portugal, Spain, Sardinia, Africa, Algeria, and Canary Islands, Asia, from Turkey to Japan to northern India. Scientists estimated auroras were visible at magnetic latitudes as low as 26, rivaling historical accounts from the Carrington event by one measure. These were among the strongest auroras in 500 years. On October 15, 2024, NASA and NOAA made it official. The sun had reached a solar maximum. But there's a critical caveat. This doesn't mean activity has peaked. The exact month of maximum won't be identifiable until at least 7 months after a consistent decline begins. Solar cycles can have double peaks, with activity rising and falling before rising again. The announcement simply confirmed we're in the maximum phase, in the most dangerous period. Recent violence. October 2024, X7.1 flare, October 1st. X9.0 flare, October 3rd, among the strongest of the cycle. November 4, 2025. 2 X-class flares in less than 12 hours, causing radio blackouts across the Americas and Pacific. November 11, 2025. X5.1 flare from R4 to 7.4, the strongest of 2025, triggering R3 level radio blackouts across Africa and Europe. December 2025. Active regions. AR-429-44296 revealed a dark patch more than 10 Earthwids across the largest in a decade. Solar physicists are tracking several concerning factors. Activity exceeding forecasts by 30% plus. Our prediction models clearly don't fully understand solar dynamics' complex magnetic configurations. Current sunspot groups show tangled magnetic fields prone to explosive reconnection. Extended maximum period. Historically, dangerous storms can occur years after official maximum. Multiple CMEs in quick succession. Rapid-fire eruptions can clear paths for faster, more powerful following CMS. The 2012 near miss nobody talks about. 10 July 2012. A massive CME erupted from the sun that would have produced a Carrington-class storm, possibly worse. The magnetic structure, speed, and intensity were comparable to the 1859 event. It missed Earth by approximately 9 days of orbital distance. We were extraordinarily lucky. The CME sailed harmlessly through space where our planet had been just a week earlier. A 2013 study estimated that if the 2012 CME had hit Earth, the economic impact would have exceeded $2 trillion. With recovery taking 4 to 10 years in some regions, we dodged a civilization-altering bullet, and most people never knew the gun was fired. What this means: Solar Cycle 25 has proven 3 things. We can't reliably predict solar activity. Our models failed significantly. The sun can still produce historic storms. May 2024 demonstrated continued capacity for severe events where not as prepared as we think. GPS disruptions, satellite issues, and communication problems revealed ongoing vulnerabilities. The cycle is expected to remain elevated through 2025 to 2026, meaning the danger window is still open, possibly for years, and somewhere on the sun's surface right now. Magnetic field lines are twisting, building energy for the next eruption. To understand the threat, We must understand the weapons deep within the sun. In the convective zone, extending from about 200,000 kilometers below the surface to the photosphere, plasma rises and falls in constant motion. This churning, combined with the sun's differential rotation equator spinning faster than poles, generates powerful electric currents. These currents produce the solar magnetic field, but unlike Earth's relatively stable field, the sun's field becomes increasingly tangled and stressed over time. Imagine winding a rubber band around your finger, tighter and tighter, until something has to give. When magnetic field lines become too twisted, they reconnect in different configurations, explosively releasing stored energy. This is magnetic reconnection, the engine driving solar flares. A solar flare is an explosion spanning the entire electromagnetic spectrum, from radio waves to gamma rays. The process: twisted magnetic field lines approach each other, they break and reconnect in a lower energy configuration. The released energy heats plasma to tens of millions of degrees. Particles accelerate too near. Lightspeed electromagnetic radiation blasts outward in all directions. The most energetic flares release energy equivalent to millions of nuclear weapons. Seconds. Scientists classify flares by X-ray intensity: A class, weakest, barely detectable above background class, slightly stronger. Minimal effects class, common during active periods. Minor radio disturbances class, moderate events causing brief radio blackouts. An astronaut. Radiation risks class, most powerful, capable of causing widespread disruption. The X-class scale works like the Richter scale. X2 is twice as powerful as X1. X10 is 10 times more powerful, with no upper limit. Solar cycle 25 has produced flares exceeding X9. When an X-class flare erupts facing Earth to 0 minutes, flare occurs on Sun 8 minutes. Electromagnetic radiation arrives at Earth, traveling at light speed, 8 to 15 minutes. X-rays and UV radiation ionize Earth's upper atmosphere. Result: radio blackouts lasting minutes to hours. Depending on intensity, radio blackout scale R1, R5, R1 minor. Brief HF radio disruption on sunlit cider 3 strong. Wide area HF radio blackout for approximately 1 hour or 5 extreme. Complete HF communication blackout for hours, affecting aviation, maritime, emergency services. While flares are dangerous, CMEs are civilization threatening. ACME is a massive bubble of magnetized plasma ripped from the sun's corona and hurled into space. A single CME can contain billions of tons of material. Magnetic fields frozen into the plasma speeds, ranging from 250 kilometers per second to over 3,000 kilometers s, the fastest. CMEs can reach Earth in less than 18 hours. Carrington was 17.6 hours. Closing parenthesis. Unlike flare radiation, instant. CMEs take time, 0 to 24 hours. CME launches from Sun, 18 to 72 hours. Transit through space, typical, 2 to 4 days, 30 to 60 minutes before impact. Spacecraft at L1 point detect approach impact. CME collides with Earth's magnetosphere. This delay is critically lit, our warning window. Here's what determines damage severity. Magnetic field orientation. Earth's magnetic field points northward at the equator. When a CME arrives, northward CME field tends to slide around magnetosphere. Relatively mild storm southward CME field. Opposite to Earth's field explosive reconnection. Cursethward, pointing CME fields open pathways for solar plasma and energy to pour into near-Earth space, transferring enormous energy into the magnetosphere. Geomagnetic storm Skalek index 0 to 9, or NOAA G scale, G1, G5, G1 minor, weak power grid fluctuations. Minor satellite effects G3 strong. Voltage irregularities. Satellite operators take corrective action. G5 extreme widespread voltage control problems. Complete HF radio blackout. Satellite damage potential. Different technologies face different threats. Satellites. High energy particles penetrate. Spacecraft electronics bit flips in computer memory cause software failures. Permanent hardware damage from radiation. Atmospheric expansion increases drag on low orbit satellites. Altering trajectories. Magnetic environment confuses attitude. Control systems. Power grids. When geomagnetic storms disturb Earth's magnetic field, they induce electric currents in the ground. These geomagnetically induced currents, Geises, flow through any conductive path including power transformer. Grounding systems, Geises, can push transformers into saturation, cause overheating, destroy core windings. Permanent damage, create cascading failures across interconnected grids. Vulnerability factors, storm intensity and duration. Transformer design and age. Illogical ground conductivity. Canada shield equals worst case. Transmission line length and orientation. North-south most vulnerable GPS systems. Solar storms make the ionosphere turbulent and unpredictable. GPS signals passing through experience varying delays, introducing positioning errors. During the May 2024 storm, John Deere reported customers using GPS-guided tractors experienced significant disruptions. Precision farming requires centimeter-level accuracy. Storm-induced errors made automated operations impossible. Aviation, HF radio blackouts over oceans and polar regions. Increased radiation exposure on polar routes. Some airlines reroute during intense events. Events understanding equals defense. We can't stop the sun from producing flares and CMEs, but understanding these mechanisms reveals opportunities for protection. Design more resilient systems, implement protective procedures, monitor activity, and prepare for incoming storms. Use warning windows effectively. The sun will continue its cycles. Magnetic fields will continue twisting and reconnecting. The question isn't whether another powerful storm will strike, it's whether we'll be ready, and to understand what ready means, we need to imagine what happens when we're not. Imagine this scenario. It's not science fiction, it's science projection. Hour 0, 3:14 a.m. You wake to absolute darkness and silence. No streetlight glow through curtains. No refrigerator hum. No LED indicators on any device. Complete darkness. You reach for your phone. 3:14 a.m., 42% battery. Good, you'll have light for a few hours. You assume a local transformer blew. Crews are probably already working. By morning, everything will be normal. But morning comes, and power doesn't return. Nor by noon, nor by evening, nor the next day or the next week. This is what catastrophic grid failure looks like from the inside, not dramatic explosions, but creeping realization that the invisible infrastructure you depended on without thinking has simply stopped working. First 24 hours, confusion. Most people still think it's temporary. News spreads slowly without internet or TV. Battery-powered radios provide some information, but details are scarce. Officials urge calm, saying crews are assessing damage. Your phone battery dies. Cell towers, running on backup batteries, continue working for 8 to 12 hours before going dark. You lose communication ability beyond shouting distance. Stores experience panic buying. Credit cards don't work. Their authorization systems are down. Cash becomes the only currency, but most people don't keep significant cash. Stores can't restock because warehouses and distribution centers have no power. Gas stations can't pump fuel without electricity, even though gasoline is in underground tanks. Your car has half a tank. You decide to conserve it. Day 2 to 3. Realization: water pressure begins dropping. Municipal systems require electricity to operate pumps, filtration, and chemical treatment. Most systems maintain pressure for hours after power fails, but eventually it drops to zero in tall buildings. Water stops flowing to upper floors first, then lower floors. Eventually, no water comes from any tap. Without power, sewage pumping stations can't move waste through the system. Gravity drains sewage for a while, but the system backs up. Raw sewage begins overflowing from manholes. Disease risk increases dramatically. Refrigerated food spoils. Meat, dairy, produce frozen goods safe to eat within 24 to 48 hours. Only shelf-stable foods remain viable. But how much do you have? Week 1. Desperation hospitals face impossible choices. Backup generators designed for 24 to 72-hour operation have exhausted fuel supplies. Ventilators stop. Dialysis machines go silent. Surgical suites close. Heart monitors flatline not because patients died, but because the monitors died. Without refrigeration, medications requiring cold storage insulin, many vaccines spoil. Pharmacies can't dispense electronic prescriptions. Life-sustaining treatments stop. People with home medical equipment, concentrators, CPAP machines, home dialysis face immediate risk. Week 2 to 4, breakdown the food supply chain has completely collapsed. Grocery stores were stripped clean within days. Warehouses have no refrigeration, and transportation networks have no fuel. Most people have exhausted home food supplies. Hunger becomes widespread. Those who prepared with emergency supplies become targets. Water shortages lead to dehydration. Disease from contaminated sources and sanitation crises. Waterborne diseases spread rapidly. Water shortages lead to dehydration, disease from contaminated sources, and sanitation crises. Waterborne diseases spread rapidly. Financial systems remain paralyzed. ATMs don't work. Banks can't access account information. Electronic transfers, the lifeblood of the modern economy, are impossible. The complex web moving trillions daily has simply stopped. Month 2 to 3. Societal collapse without fuel. Transportation ceases. Without transportation, regional food supplies, even non-perishable, can't be distributed. Rural areas with local food sources fare better than urban centers. Communication remains down. You don't know what's happening beyond your immediate area. Is it the whole country? The continent? The world? Is help coming? Is anyone in charge? Civil order becomes strained. Emergency services can't function without fuel, communication, or coordination. Crime increases. Vulnerable populations suffer most. In northern latitudes, seasonal weather becomes a deadly factor. Winter without heating, summer without cooling for the elderly and ill. The scale of catastrophe, this scenario, isn't speculation. It's based on studies analyzing severe geomagnetic storm impacts. 2008, National Academy of Sciences. Study, Carrington class. Event could damage, destroy 300+ large transformers across the U.S. Blackouts affecting by million people. Duration. Months to 10 years in some areas. Economic cost. $1 to $2 trillion in first year alone, 2013. Lloyd's of London analysis. Potential U.S. cost, $600 billion to $2.60 trillion. These figures don't include human costs and lives lost. 2020. Economics of disaster study. Severe storm disrupting industrial production, would also disrupt agricultural inputs, fertilizers. Pesticides, global crop yield reductions, 38 to 48%. Some regions, Central Europe, up to 75%. Yield losses. Why this is different and like earthquakes, hurricanes, or floods which cause localized destruction. A severe geomagnetic storm affects entire continents simultaneously. There's no unaffected neighbor to call for help. Everyone faces the same crisis at once. The interdependence trap. Modern infrastructure is deeply interdependent. Power plants require fuel deliveries, transportation. Networks. Transportation requires fuel. Refineries with electricity. Refineries require electricity to operate. Communication systems coordinating response require power. Each system depends on others that also depend on power. When the grid fails, everything fails. Geographic vulnerabilities. Some regions face greater risk. Highest risk, northeastern U.S. and eastern Canada. Geology. Grid configuration. Scandinavia, northern latitude. Geology. Parts of China and Japan. Past transformer damage from storms. Factors, long transmission lines. Low ground conductivity forces currents into power lines. Older transformer designs northern latitudes stronger. Geomagnetic disturbances, the good news we're not helpless. Engineers have developed protective technologies, neutral blocking devices, prevent GICs from entering transformer windings, protective relays, detect GIC signatures, and take defensive action operational procedures, reduce power flows and disconnect vulnerable equipment when storms approach, spare equipment stockpiling, reduces recovery time. The bad news: implementation is uneven. Some grids are well protected. Others remain vulnerable. The patchwork nature means severe storms can still find weak points to exploit. We've built civilization on electricity. We've designed the grid for efficiency and economy, not resilience against space weather. We've created interdependencies so complex that failures in one sector cascade rapidly into every other sector. The question isn't whether the grid could fail catastrophically. It absolutely could. The question is what we're willing to do to prevent it, and to understand why prevention is possible. We need to explore the invisible shield that's been protecting us all along, every second. The sun hurls approximately 1 million tons of charged particles into space. This solar wind races through the solar system at speeds exceeding 1 million miles per hour, carrying the sun's magnetic field twisted into a vast spiral extending beyond Pluto. If this relentless bombardment struck Earth directly, the consequences would be catastrophic over geological time. The charged particles would strip away our atmosphere just as they stripped Mars billions of years ago. Radiation would make the surface uninhabitable. Earth would be a dead world, oceans boiled away, surface scoured by unfiltered stellar fury. But we are protected, and that protection comes from deep within our planet. The geodynamo, approximately 1,800 miles beneath your feet, surrounding Earth's solid iron inner core, lies a layer of liquid iron and nickel. This outer core churns and flows, driven by heat escaping from the inner core and planetary rotation. The movement of this electrically conductive fluid generates powerful electric currents, which produce Earth's magnetic field. This geodynamo has operated for at least 3.5 billion years. The magnetosphere's magnetic field extends far into space, creating a vast bubble called the magnetosphere, sunward side, compressed by solar wind pressure to approximately 40,000 miles night side, stretched into a long tail, extending millions of miles. Like a comet's tail, the magnetosphere isn't a solid barrier, it's a region of space, dominated by Earth's magnetic influence rather than the sun's. When solar wind particles approach, they encounter this magnetic bubble and are deflected around it. Flowing along the boundary like water around a rock in a stream, the polar advantage some particles do penetrate, particularly near the poles, where magnetic field lines converge and dip toward the surface. These particles spiral down field lines into the upper atmosphere, colliding with gas molecules and producing auroras. The northern and southern lights are visible proof our shield is working, channeling dangerous radiation into harmless beauty. The Mars comparison. Mars tells us what happens without this protection. Mars once had a global magnetic field generated by a molten core similar to Earth's, but Mars is smaller and cooled faster. Approximately 4 billion years ago, the Martian core solidified. The dynamo shut down. The magnetic field collapsed, exposed to the full force of solar wind. Mars lost its atmosphere over billions of years, molecule by molecule. Today, atmospheric pressure, less than 1% of Earth's surface. Bathed in radiation, liquid water cannot exist on surface if life ever existed on Mars. The loss of its magnetic field may have been a death sentence. Direct comparison in 2008. Scientists used data from spacecraft at Earth and Mars during the same solar wind event. When both planets were hit by identical solar streams, Mars lost atmospheric oxygen at 10 times the rate Earth did. That's the magnetosphere, at work reducing impact by an order of magnitude. Over billions of years, that difference means the difference between life and death. Atmospheric layers. The magnetosphere is only the first defense layer. Earth's atmosphere provides additional protection. ozone layer stratosphere. 10 to 30 miles, absorbs a vast majority of UV radiation without it. Surface life would be impossibly ionosphere upper atmosphere. Absorbs X-rays and extreme UV from solar flares dense lower atmosphere. Provides protection against cosmic rays and energetic solar particles through collision cascades. Layered shielding is why solar storms don't directly harm people on Earth's surface. Radiation is absorbed or deflected long before reaching us. The threat is to technology, not bodies. Astronauts and pilots beyond the dense atmosphere. Exposure increases. ISS astronauts take shelter in heavily shielded sections. During intense storms, polar flight crews receive elevated radiation doses. Some airlines reroute during storms. Future Moon-Mars missions. Radiation protection will be critical design consideration. The changing shield. Earth's magnetic field isn't constant. It fluctuates in strength and has reversed polarity many times throughout history. Most recent reversal, Brunsma-Tuyama. 780,000 years ago, during reversals, the field weakened significantly before reorganizing with opposite polarity. Some scientists speculate we might be in early stages of another reversal. The field has weakened approximately 9% over the past 200 years. A weakened field during a powerful solar storm could allow more radiation to reach. Surface increase intensity of geomagnetically. Induced currents expand vulnerability. Zones toward equator. Life has survived many reversals, but we've never experienced one during the technological age. The South Atlantic anomaly, weak spot, exists right now over South America and the southern Atlantic Ocean, where the magnetic field is significantly weaker. Satellites passing through experience elevated radiation levels. The Hubble Space Telescope routinely shuts down instruments while traversing the anomaly. The anomaly has been growing over recent decades. A second weak spot may be developing over Africa. Scientists monitor these changes, though there's no consensus on whether they indicate imminent reversal or normal fluctuation. Our invisible shield has protected life for billions of years, allowing evolution to produce the diversity we see today. It continues protecting us. It's deflecting the worst solar wind while allowing enough through to create beautiful auroras. We did nothing to earn this protection. It's a gift of geology and physics, a consequence of Earth's size, composition, and internal heat. But it cannot protect our satellites, power grids, or technological infrastructure. That protection is our responsibility. Which brings us to the darkest question. Could the sun actually end human civilization? Could it end life on Earth entirely? These aren't comfortable questions, but we need honest answers. The direct threat assessment. Short answer. The sun, as it exists today, cannot produce an event that would directly exterminate all life on Earth. Our magnetosphere and atmosphere provide protection that no solar storm can fully overcome. Even the most extreme events, our sun, could produce wouldn't boil away oceans or sterilize the surface to bedrock. But that's not the only way the sun could threaten human existence. The Carrington baseline, Carrington 1859, remains the largest solar storm in recorded history. If it struck today, widespread power grid and satellite damage, economic impact, trillions of dollars human cost from failed infrastructure. It's potentially significant, but civilization would survive and rebuild. Carrington-level events occur approximately once every 100 to 200 years. The 2012 near Mistily, 2012, a massive CME erupted that would have produced a Carrington-class storm, possibly worse, famed at Earth. It missed by 9 days of orbital distance. We were extraordinarily lucky. Most people never knew how close we came. The Miyake-Evans carbon-14 spikes in ancient tree rings reveal far more powerful events. 774-775 CE. 10 to 20 times stronger than Carrington 993 to 994 CE. Somewhat weaker, but still extreme. 7,176 BCE and 5,259 BCE. Additional mega-events. Discovery of multiple such events in the past 10,000 years suggests they're more common than previously believed, potentially once per millennium. Miyake impact, we honestly don't know with certainty what a Miyake-class event would do to modern civilization. Our models are based on weaker storms. Extrapolating to events 10 to 20 times more powerful introduces significant uncertainty. Probable outcomes: overwhelming many current protective measures, widespread grid failures beyond design parameters, satellite damage far exceeding hardening specifications, more widespread, severe and difficult recovery, the civilization collapse scenarios. Some researchers suggest an extreme solar event could damage enough global electrical infrastructure to trigger cascading industrial civilization collapse. Without electricity for months or years, food manufacturing, transport, distribution fails, water treatment and distribution fails, communication networks coordinating complex societies fail, prolonged global blackout could result in casualties numbering hundreds of millions or more, not from direct solar radiation, but from collapse of technological systems supporting 8 billion people on a planet that couldn't naturally support nearly that many. The sun wouldn't kill us directly. It would kill the machines we depend on. Superflare possibility astronomers have observed other sun-like stars, producing superflares thousands or even millions of times more powerful than anything our sun has produced in recorded history. The question, is our sun capable of such events? For years, scientists believed our sun was too stable. But some superflare-producing stars have activity levels comparable to or lower than our Miyake events proved our sun produces events far stronger than modern records. The possibility can no longer be entirely dismissed. Frequency estimates: Harvard researchers estimated extinctional level superflares powerful enough to significantly erode atmosphere or severely damage the ozone layer occur approximately once every 20 million years. Rare on human timescales, but certainly has happened multiple times in Earth's history. Controversial hypothesis: some scientists have proposed extreme solar events may have contributed to past mass extinctions. One hypothesis suggests a supersolar proton event approximately 12,800 years ago could have played a role in Pleistocene megafauna extinction. Evidence is controversial and not widely accepted, but illustrates researchers are taking seriously the possibility of biologically significant solar events. The extreme scenario: at the theoretical extreme, a sufficiently powerful superflare could damage Earth's ozone layer, allowing increased UV radiation to surface inject massive nitrogen oxides into stratosphere. Further depleting ozone trigger climatic effects, produce radiation levels posing direct surface health risks. But even these extreme scenarios wouldn't sterilize the planet. Life has survived worse. The asteroid impact that killed the dinosaurs was far more destructive than any plausible solar event. The real threat, isn't extinction of all life. It's potential disruption or collapse of human civilization. We've built a world depending on constant electricity, continuous communication, and global coordination. We've created systems so complex and interconnected that failures cascade unpredictably. A severe solar storm wouldn't kill everyone directly, but it could kill the systems keeping everyone alive. That's a distinction that may not matter much to people caught in the collapse probability assessment Carrington-class event in next decade, approximately 1 to 12%. Chance of Miyake-class event in any given century, harder to estimate but clearly not zero. Civilization event in our lifetime, low but not negligible. We can't prevent solar storms. We can only prepare, building resilience and developing rapid recovery capability. The sun won't end all life on Earth, but it could end life as we know it. The difference between those outcomes depends entirely on what we choose to do now. The sun doesn't give much warning. A solar flare erupts, radiation arrives in 8 minutes. A CME launches, we have perhaps 1 to 3 days before impact. Final confirmation of intensity comes just 30 to 60 minutes before it hits. Not much time. The Early Warning Network, the Space Weather Prediction Center in Boulder, Colorado, operates the 24th of July 365. Forecasters monitor data streaming from a fleet of spacecraft. NASA's Solar Dynamics Observatory, high-resolution solar surface imagery SOHO satellite, coronagraph imaging of CMS and OAA GOES satellites, geostationary monitoring DSCO-VR at L1, real-time solar wind monitoring when a potentially dangerous event occurs. The center issues alerts too. Power grid operators, satellite operators or lines. Polar. Root impacts, emergency managers, military and government agencies. L1 advantage in OAAs, Deep Space Climate Observatory, DSCO-VR. Positioned at the L1 Lagrange point, approximately 1 million miles sunward of Earth, it provides the critical final warning. When a CME arrives at DSCO-VR, sensors measure speed, density, magnetic field orientation, the critical factor this data transmits to Earth, giving operators 30 to 60 minutes of warning in-off, time for emergency procedures, grid protection procedures, power. Grid operators have developed operational protocols for space weather events. When severe storm expected, reduce power flows on vulnerable transmission lines, bring additional generation capacity online for stability suspend maintenance activities. That increase vulnerability position, crews and equipment for rapid damage response increase. Monitoring frequency, the Hydro-Quebec success story after the devastating 1989 blackout. Hydro-Quebec invested $2 billion in protective improvements raised. Trip levels on protective relays, installed series compensation on transmission lines, established real-time geomagnetic monitoring, developed procedures to reduce power before damage occurs. Our result: multiple intense storms since 1989, some approaching or exceeding 1989 intensity without similar blackouts. The modern system can handle in 100-year events. Hardware solutions, neutral blocking devices. Install at transformer bases to prevent GICs from flowing through windings. Insert a capacitor in the neutral connection, blocking quasi-DC induced currents while allowing normal AC flow. Success story: Western Area Power Administration installed its first device at Witt Substation, South Dakota in November 2022. During a moderate storm in February 2023, the device activated automatically, successfully protecting the transformer. The technology works. The challenge is deploying it widely enough. Spare transformers, stockpiling large power transformers. It's difficult to manufacture, specialized facilities, expensive, tens of millions each, long lead time. 12 to 18 months under normal circumstances during crisis, affecting multiple utilities. Timeline grows longer. Having spares already positioned dramatically reduces recovery time. Satellite protection: the satellite industry has developed protective measures. Safe mode during intense storms, shutting down sensitive instruments, orientation to minimize radiation, exposure, delaying sensitive maneuvers until storms pass, improved. Electronics designs more resistant to radiation-induced failures, GPS enhanced monitoring during solar storms. Enhanced monitoring of ionospheric disturbances, warnings issued when positioning accuracy degraded. Some applications automatically fall back. 2 alternative navigation alerts to users depending on high precision. International coordination: International Space Environment Service brings together space weather agencies worldwide to share data and coordinate warnings. UN Committee on Peaceful Uses of Outer Space recognizes space weather as global concern, requiring international cooperation. When a severe storm threatens Earth, it affects the entire planet. Response must be equally global. National Strategy: United States. A national space weather strategy coordinates efforts across agencies. NASA, research, and improved solar physics. Understanding, AOA, forecasting and warning systems, DHS, works with critical infrastructure operators. On resilience, DOE supports grid protection technology research, FOMS, for widespread damage individual preparedness, households. Maintaining supplies will weather prolonged outages better. Water, 1 gallon per person per day. 2-week supply, non-perishable food, 2-week supply. Batteries and battery-powered devices, cash electronic transactions will fail. First aid. Supplies, medications. 30-day supply if possible. Communities identifying vulnerable populations and developing assistance plans will recover more quickly. Improvements since 1989 have addressed moderate to strong geomagnetic storms. They haven't fully addressed extreme events like Carrington or worse. Protecting North American grid against Carrington-class event. Its estimated cost of several $billion. Small fraction of potential damage, but still substantial investment. Progress has been incremental, driven more by individual utility decisions than comprehensive national policy.
Oh.
Some grid sections are well protected. Others remain vulnerable. Supply chain vulnerability. Global manufacturing capacity for large power transformers is limited. Most are custom-built for specific applications. A severe storm, damaging hundreds, simultaneously would create a shortage taking years to resolve. Beyond our model's hour, protective standards are based on what we've observed and can simulate. A Mioka class event far more powerful than anything in modern records might overwhelm systems designed for lesser storms. We're preparing for events we've experienced or can imagine. We may not be prepared for events exceeding our imagination. The ongoing work. New satellites being developed with improved monitoring capabilities, forecasting models being refined with better physics and more data. Grid operators implementing new protective measures. Response procedures being tested. Scientific community studying ancient records to understand the full range of possible events. Where making progress. We're better prepared today than in 1989. We'll be better prepared tomorrow than today. But the sun doesn't grade on a curve. It doesn't care whether we've done our best. When the next great storm comes, we'll either be ready or we won't. The warning systems will give us hours or days of notice. What we do with that notice depends on preparations we make now. Technology and infrastructure are only part of the equation. The human element. Policy, investment, sustained attention determines whether we'll be ready. The investment question: how much should we invest to protect against a threat that may not materialize in our lifetimes, but almost certainly will eventually? This is fundamentally a question about valuing future generations equally with current ones, accepting costs now for benefits that may arrive decades or centuries later. Planning for events can't predict with precision. The political challenge space, whether preparedness requires sustained commitment across timescales longer than political cycles and quarterly reports. Politicians face pressure to address immediate visible problems. Solar storm preparation doesn't produce ribbon-cutting ceremonies or immediate voter gratitude. Yet the consequences of failure: cascading infrastructure collapse, economic devastation, potential loss of life, dwarf the investment required. The generational question: where making decisions whose consequences future generations will experience. If we prepare adequately and no major storm occurs in our lifetimes, future generations will never know the catastrophe we prevented. If we fail to prepare and a major storm strikes, they'll wonder why we didn't act when we clearly understood the threat. Community resilience. While large-scale infrastructure protection requires government and utility action, community-level resilience matters. Effective communities identify vulnerable populations: elderly, disabled, medically dependent, develop mutual aid networks, establish emergency communication plans that work without electricity, organize emergency response training, create local resource sharing agreements during extended blackouts. Communities with strong social connections and organized response plans fare significantly better. Personal responsibility, individual preparedness can't solve systemic infrastructure failure, but it provides a buffer. Realistic home preparation, 2-week supply of water and non-perishable food, battery-powered, or hand-crank radio flashlights and batteries. First aid kit, prescription medication, reserves, cash reserves. Electronic transactions will fail. Copies of important documents. Know your neighbor's social connection is critical. This doesn't prepare you for years-long blackouts, it prepares you to survive the critical initial period while organized response develops. The education gap. Most people have no idea that solar storms pose a serious threat to modern infrastructure. The general public doesn't understand what geomagnetic storms iridescent, know about historical events like Carrington or Quebecise, isn't aware of vulnerabilities in power grids and satellitation. Considered what prolonged widespread blackout would mean. Education is essential. An informed public supports necessary investments and preparedness measures. The economic argument cost-benefit analysis strongly favors preparation. Investment required, several $billion. U.S. grid hardening potential damage, $2 minus 3 trillion. Economic impact, years-long recovery, potential casualties in millions. The return on investment is obvious. Progress remains slow. Corporate responsibility. Private sector owns much critical infrastructure. Utility companies own transformers and transmission lines. Satellite companies own spacecraft vulnerable to radiation tech. Companies operate data centers and communication networks. Corporate decisions about resilience investments significantly impact societal vulnerability. Short-term profit pressure versus long-term societal risk creates tension. International equity. Developing nations have fewer resources for protection but face equal or greater risk. Less robust infrastructure is more vulnerable. Less reserve capacity. For emergency response, fewer resources for rapid recovery. Greater dependence on international aid that may not be available if storm affects entire hemisphere. Global coordination and support are not just ethical imperatives, they're practical necessities. In an interconnected world, the window where currently in solar maximum of cycle 25, activity will remain elevated through 2025 to 2026, possibly longer. This is both a danger window and an opportunity window. If a major storm strikes soon, it will focus attention and resources on the problem. If the cycle passes without major incident, attention may wane again. We can't control the sun's timing, we can only control our response. The choice is ours. Pay smaller costs now in preparation, or pay catastrophic costs later in disaster and recovery. The clock is ticking. The sun doesn't wait. The sun rose this morning, as it has every morning for 4.6 billion years. It will rise again tomorrow, and for another 5 billion years until it exhausts its hydrogen fuel and transforms into a red giant that consumes the inner planets. On cosmic timescales, the sun is stable and predictable, the most reliable force in our existence. On human timescales, it's a nuclear furnace with violent mood swings, occasionally hurling billion-ton plasma bombs across 93 million miles of space toward our fragile technological civilization. What we've learned today, it synthesized what we've discovered. 1. The historical evidence. The Carrington event of 1859 demonstrated the sun can reach across space and affect Earth's technology. The 1989 Quebec blackout proved solar storms can collapse modern power grids in 90 seconds. The 2012 near myth showed we came within 9 days of a civilization-altering disaster. Ancient records reveal storms far more powerful than anything in modern experience, too. The current threat. Solar cycle 25 has exceeded all predictions. We're in solar maximum now. The most dangerous period. Recent storms, May 2024 G5 event, have demonstrated continued vulnerability. Massive sunspot regions, currently visible, pose ongoing risk. 3. The science. Solar flares travel at light speed. 8 minutes from sun to Earth. Coronal mass ejections take 18 to 72 hours, giving us critical warning time. Magnetically induced currents can destroy power transformers. Cascading failures spread faster than humans can respond for. The potential consequences. Crink-class event today, trillions in damage. Months 2 years. Recoveramia class event, potential civilization disrupting impacts. Prolonged widespread blackouts trigger cascading failures in water, food, medical care, communication. 5. The protection. Earth's magnetosphere provides first-line defense. Atmosphere absorbs most radiation, but technology remains vulnerable. Warning systems, protective devices, and operational procedures can significantly reduce damage. 6. The preparation. Gapewe've made progress since 1989, but protection is uneven and incomplete. Many grids remain vulnerable to extreme events. Investment hasn't matched the scale of potential risks. The choice before us. We stand at a crossroads. We've built a globally connected, electricity-dependent civilization in just over a century. This civilization is vulnerable to a natural phenomenon we've understood for barely 170 years. We have the knowledge to protect ourselves. We have the technology to harden infrastructure. We have warning systems to provide notice before storms arrive. What we sometimes lack is the will to act. The probability of a civilization threatening a solar storm in any single year is small. But over decades and centuries, those probabilities accumulate. History tells us extreme events happen. Physics tells us they'll happen again. The question isn't if, it's when. And when that day comes, we'll either be ready or we won't. What can be done at the policy level? Comprehensive, national, and international. Space weather strategies, mandated protection. Standards for critical infrastructure investment in transformer stockpiles and rapid replacement capabilities, expanded satellite monitoring and forecasting capabilities, international cooperation and data. Sharing at the utility level. Deployment of neutral blocking devices on vulnerable transformers, implementation of operational procedures for storm. Response hardening of critical infrastructure, spare equipment positioning, regular testing and training at the community level. Emergency response planning. Identification and support systems for vulnerable populations, mutual aid networks communication. Plans that work without electricity at the individual level. Basic emergency preparedness. Water. Food, medical supplies, understanding the risks, supporting policies and investments that increase resilience, building community. Connections. The cosmic perspective. We are a technological species living on a small planet orbiting an ordinary star in an average galaxy. We've built something remarkably civilization, connecting billions of people, sharing information instantaneously, collaborating on challenges that would have seemed impossible to our ancestors, but we remain vulnerable to the very star that gave us life. This isn't a reason for despair, it's a reason for action. Understanding the threat is the first step toward addressing it. We're not helpless. We're not doomed. We simply need to take the threat seriously and invest appropriately in protection. The sunspots watching us right now will disappear in days or weeks, replaced by new ones. The cycle will continue. The sun will keep churning, building and releasing magnetic energy, utterly indifferent to the civilization in its path. The question is whether that civilization will still be there when the next great storm arrives. Your role in this story: if this video opened your eyes to a threat you didn't know existed, you're part of the solution. Share this knowledge. Talk about it. Support policies and investments that protect critical infrastructure. This is not someone else's problem. This is a shared human challenge that affects every person on this planet. Before you go, if you found this deep dive valuable, show some love. Smash that like button to help others discover this critical information. To the Cosmic Atlas and hit notifications. We're diving deep into the cosmos's most compelling mysteries every week. Share this video with someone who needs to understand this threat: your family, friends, community leaders. Drop a comment telling me what cosmic topic should we investigate next. The supervolcano sleeping beneath Yellowstone. The asteroids silently crossing Earth's orbit. The mysterious deep ocean we've barely explored. Or something else entirely. Next episode, we're diving into another invisible threat most people don't think about, but should. It's closer than the sun, more certain than solar storms. We're running out of time to address it. You won't want to miss it. The sun will rise tomorrow. It will rise on a world that either prepared for its Furrier D in single quotes. The choice is ours. The time is now. Thank you for joining me on this journey through the cosmos. Until next time, keep looking up, but also keep preparing for what might come down. This is the Cosmic Atlas, reminding you that understanding the universe isn't just about wonder, it's about survival. Stay curious, stay informed, stay safe.